Hello, everyone. I'm Yupeng Zhang from the University of Maryland. Today, I'm going to present our paper, SecureML, a system for scalable privacy-preserving machine learning. This is a joint work with a payment from Visa Research. Machine learning is used everywhere these days and always leads to breakthroughs in a lot of areas. For example, it can be used for image processing, speech recognition, fraud detection, and even playing the game Go. And the reason why it performs so well in practice is because we use a large amount of data to train these machine learning models. Okay? And despite of these great breakthroughs, it also leads to security issues. Namely, how do we protect the privacy of our data? So to clarify this privacy is something different from the previous talk. Here we're considering the privacy of the data used for the training purpose. Because as an end user, we do not want to share our sensitive information with big companies for them to run the machine learning algorithms. Okay? So how do we solve this problem? Privacy-preserving machine learning provides a solution for this security issue. It enables a company to still perform the same machine learning algorithm without knowing the underlying content of users' data. So in this way, we can still gain the benefits of machine learning while protecting our data privacy without leaking the information to the companies. And there are a lot of great prior work in the literature of privacy-preserving machine learning, and some of them are listed on the slide. And this is a very active line of research. So in particular, in our paper, we focus on the following security model called two-server model. In this model, we assume there are two servers that belong to two different companies, and they do not collude with each other. As an end user, we will first split our data into two shares and send each share to one server. In this way, a single server cannot learn anything about the original data because he only have access to a single share. After that, the two servers interact with each other to perform a two-party secure computation and generates the model. Okay? And the benefits of this security model is that first, it reduces the problem from multi-party computation to two-party computation, which improves the efficiency significantly. Second, the users can go offline after submitting the data and do not need to interact with the servers during the training. In addition, it also captures the scenario where the two companies want to jointly train a model without sharing their data with each other. And the model is widely used in many prior work. So the contribution of our paper is that under this security model, we propose new protocols for privacy-preserving linear regression, logistic regression, and neural networks. In particular, we are using a combination of secret sharing and arithmetics on shared values with pre-computed triplets, plus Scalable circuits. On the implementation side, we show that our system is orders of magnitude faster than prior work and scales to large datasets with up to 1 million records and 5,000 features. And in this talk, I'm going to focus on linear regression and logistic regression, and the techniques can be generalized to train neural networks, and you can refer to our paper for more details about it. So first, what is linear regression? Imagine we draw the data points and their corresponding values on a plane like this. Then linear regression is trying to fit a line across these data points. Okay? More formally speaking, the input is the data value pairs of x and y. Here, x can be a vector and is also known as features, and y is a single value for value, and also known as a label. The output model W is defined by a vector of coefficients that has the same dimension with the input x, such that the inner product between W and x should be approximately equal to the value y. This defines a linear relationship between x and y. To train the model, here I'm introducing an algorithm called stochastic gradient descent. SGD. It views the problem as an optimization problem, trying to find the best model W to minimize the distance between y star and y. And it begins by initializing W at a random location, and then select a random sample from the dataset. It computes the prediction based on the current model W, compare it with the correct label, and this will tell you which direction you should move towards the optimal location. And it can be proved that if you do it repeatedly, eventually the model will converge to the optimum location. This is SGD. And in particular, for linear regression, the update function is this formula as shown on the slide. As you can see, this update formula is very simple. It only involves several multiplications and subtractions. Therefore, a natural way to do privacy-preserving linear regression is that how about we just apply the secret sharing and arithmetic on shared values directly. Okay, that should solve the problem. And the scenario is as following. The users first secret share the data and values, and the servers initialize the model W randomly and also secret share them. After that, we simply run this formula again and again using the arithmetic on secret shared values with pre-computed triplets, and problem solved. But there's a big issue here. Because secret sharing and this arithmetic only works on integer fields. For example, integers modular large prime. But the linear regression and SGD only make sense if the numbers are represented in by decimal numbers. So how can we support decimal number operations? This leads to our first contribution. We show a way to support decimal multiplications directly in integer fields. And the idea is as following. Think about there are two decimal numbers like this, and you know the plain text of them. Then you multiply them together by keeping the full accuracy. You will get a number C that doubles the size of the decimal parts, right? And here I'm assuming the integer part is big enough and does not grow. So this step is exactly the same as integer multiplication by removing the decimal points, which is good, but the size of C is keep growing. Sooner or later, it will be larger than the size of the field, and you will have overflow. So a natural way to solve this is by truncation, which means simply cut the last 16 bits of C, throw them away. Right? In this way, C has the same size of A and B, and this is, of course, known as fixed point multiplication. So in our paper, we further show that this truncation trick still works even if the numbers are secret shared. In particular, here we have A and B secret shared between the two servers, which means they're masked by a large random number in a much larger field. And then you perform multiplication using the pre-computed triplets, which gives you the shares of the result C, C0 and C1, that encodes the number with full accuracy. After that, you truncate each individual share independently without any communication. And we show that after truncation, these two shares can reconstruct to the exact same answer of fixed point multiplication, plus a small error on the last decimal bit with high probability. That's our technique. With this technique back to the protocol, after every multiplication, we simply need to perform the truncation on the shares, and that completes the whole protocol for privacy-preserving linear regression. Okay. And to show the effect of our technique, as we are only introducing a very small error on the last decimal bit, it behaves almost exactly the same as running the training on the plain text data using decimal numbers. And in particular, our technique is 4 to 8 times faster than fixed point multiplication gobble circuits in different settings. That's all for linear regression. Next, logistic regression. Logistic regression works for classification algorithms, where you're trying to divide your data points into two categories. And formally speaking, now the data value pairs is as before, and now y should be binary, either 0 or 1, representing two categories. And the difference between logistic regression and linear regression is that we want to further apply an extra function f on top of the inner product. And this f is known as the activation function. For logistic regression, the f is in this form, 1 over 1 plus e to the minus u, and the shape is shown in the plot. To train the model, we still can use SGD algorithm, and surprisingly, the update function is almost the same as linear regression, except that we apply this extra f on top of the inner product. Everything else is the same as linear regression. Which means if we have a way to compute this function f in secure computation, we can add it to the original protocol for linear regression, and that's it. But turns out this is quite challenging because the function f involves decimal exponentiations with a natural base. So how can we compute this? A traditional way is through something called polynomial approximation. And here's a plot, the curve using a degree 10 polynomial. As you can see, it's quite close to the logistic function, but it introduced a big overhead to evaluate this polynomial in secure computation because you need to use at least 10 multiplications to compute a degree 10 polynomial. Instead, in our paper, we think about what do we need from this activation function. What we really need is something bounded between 0 and 1 because it's working for classification problems, and it's increasing in the middle. So how about we use this function? Okay. We show that if using this function as activation function, we can almost get the same accuracy as the original logistic function. But more importantly, it is very efficient to evaluate in secure computation using gobble circuits. It only involves the subtraction and compare to 0, which means you take the most significant bit. Therefore, this brings us to the next contribution. We bring up a concept of secure computation-friendly activation function. Instead of approximating existing activation functions, why don't we just take a step back, think about what properties we need from these functions, and try to come up with new ones that can be efficiently computed in secure computations. Back to the protocol, as I promised before, you just run the exact same protocol for linear regression. After the inner product, we switch to gobble circuits to evaluate this function, and then switch back to run the original protocol. And that's all for privacy-preserving logistic regression. In addition, in our paper, we also introduced other optimizations like vectorization, which means everything can be represented in a matrix form. And this can improve the efficiency significantly. And also the techniques generalized to neural networks. Finally, I want to show you some experimental results. So here I'm showing you the results for 100,000 records and 500 features in each record. Our protocol can be naturally divided into two phases. The first phase is a data-independent offline phase to generate these multiplication triplets. And the second phase is the online phase to train the algorithm. In a LAN network, the bandwidth is 1.2 gigabytes per second, and the delay is 0.17 milliseconds. And the offline phase of our protocol takes around 400 seconds. And the online phase of our protocol is extremely fast. It only takes 1.4 seconds, which is only twice slower compared to plain text training. In one network where the bandwidth is 9 megabytes per second and the delay is 72 milliseconds, it takes around 9,000 seconds for offline phase and 141 seconds for the online phase. Even in the one setting, the performance of our system is 54x faster than systems in prior work. Moreover, we observe that the offline phase is the bottleneck in our systems, so we further provide an alternative way to generate these triplets with the help of the users. In this way, we can significantly reduce the offline time while increasing the online time a little bit. In addition, this also weakens the security model. Here, we further assume that the clients cannot collude with any of the two servers. Okay. Next, results for logistic regression. As I presented before, the good thing about our protocol is that the logistic regression consumes no extra pre-computed multiplication triplets compared to linear regression. Therefore, the offline phase is exactly the same as linear regression. In the online phase, we need to evaluate an extra gobble circuit and introduce an extra round of interaction, which increased online time by this much. It's still on the same order compared to linear regression. To the best of our knowledge, we are the first to implement a system for privacy-preserving logistic regression under this security model and can scale to up to 1 million records with 5,000 features in each record. Finally, neural networks. We implemented a neural network with 2 hidden layers and 128 neurons each. And here I'm presenting the end-to-end performance, including both online and offline. It takes 25,000 seconds to train this neural network in the lens setting, which has a 35 times overhead compared to plain text training. In the one setting, the performance is much worse. For this size of data set, it approximately will take 200,000 seconds in total. To sum up, in this paper, we present new protocols for privacy-preserving linear regression, logistic regression, and neural networks. In particular, we introduce a way to support decimal multiplications directly on integer fields. And we propose secure computation-friendly activation functions. And we introduce vectorization. On the implementation side, our system is orders of magnitude faster than prior work and can scale to large data sets. That's all of my talk. Thank you.
We have 2 mics for questions from the audience. So let me ask a question. So you list 3 principal techniques for improving, for adapting these tasks to the SFE setting. Mm-hmm. Can you break down what are the which technique was contributed what to the?
Yes, actually we have a very detailed micro benchmarking in the paper, and to summarize a little bit, each one individually introduced approximately 10 times speed up compared to the generic approach. But all these things must be used together. For example, this decimal thing cannot be used with gobble circuits. And it must be integrated into this arithmetic on shared values. And in total, we have speed up of several orders of magnitude.
Thank you.
Hi, John Criswell, University of Rochester. Just a simple question. For your experimental setup for the wide area network experiments, is that simulation or did you actually use a real wide area network?
Yeah, actually I implemented on the Amazon machine. One is located in US East Coast and the other one is located in US West Coast. And it's the real experiment, no simulation.
Okay, thank you.
Okay, let's thank the speaker again.